Let's start with route planning. The goal of route planning is to navigate from point A to point B. In this example here, I have planned a route through Google Maps from my work location in Tübingen to the castle of Tübingen. And we want to plan that route through a roadmap using the most efficient path, where efficiency could be specified in terms of time, travel time, or travel distance. Route planning is a high-level planning task where low-level details such as the local path or trajectory of the vehicle are abstracted away. And therefore, route planning is sometimes also referred to as mission planning. How can we actually do this? How can we plan a route through a road network? Well, first we have to actually represent the road network, and we can do this through the notion of graphs. Here you can see a road network represented as a graph. Let's zoom in a little bit. If we zoom in, we can see that we can also represent lanes in terms of graphs. So here we see nodes with arrows in between, which together form a directed graph. So we can see that the different paths we can travel through this map can be represented in the form of such directed graphs, where we have a directed graph that comprises vertices and directed edges, where the direction is indicated by these little arrows here. In this case here we have one for each of the lane, for the ingoing lane and for the incoming lane, and for the outgoing lane here we have one edge that represents a little lane segment in this case. So we've seen road networks can be represented as directed graphs both at the road level and at the lane level, depending on the granularity that we want to model them. Typically in self-driving we have HD maps, which means we have lane level information available, and that's also important, so we can actually do the planning at the lane level. But in terms of representing them in form of graphs, it doesn't matter. Both at the road or at the lane level we can represent road networks as directed graphs. So let's formalize this a little bit more mathematically now. How can we formalize this? So road networks can be represented as directed graphs. One example of a simple directed graph with just 6 vertices is illustrated here. And mathematically we can write such a directed graph as G equals the tuple v, e, where v is the vertex set and e is the edge set. And we write little v element of the vertex set if the vertex v is an element of this vertex set. And we can write a directed edge as the tuple u, v, where both u and v are element of the vertex set, and this tuple is element of the edge set e if that directed edge from vertex u to vertex v is element of that directed graph. So it's basically just two sets, a vertex set and an edge set, where the edges correspond to road or lane segments depending on the granularity we are modeling. We have two special nodes in such a directed graph, the S node and the T node, where the S denotes the source and the T denotes the sink. And we're interested in finding the shortest path through this graph from the source to the sink. In the example from before, S would have been my work location and T would have been the target, the destination, castle location. What does it mean to find the shortest path? Well, in the case of unweighted graphs, this simply means we want to find the path with the least number of edges from S to T. In this particular case, the path, not the graph. So in this particular case, all 3 paths are shortest paths. So we can go from S to A, C to T, or BDT or ADT. They are all paths with 3 edges, 1, 2, 3. Later on, we're going to see that it's often convenient to define weighted graphs, and in this case, we do not just want to find the shortest path in terms of the amount of edges that we want to traverse, but also the sum of the weights that are defined for these edges. But now let's stay still with the unweighted graphs for a moment. So how can we find a shortest path in such unweighted graphs? And the algorithm we're going to use is called breadth-first search. So how does breadth-first search works? Well, let's first introduce a data structure that we need for breadth-first search, which is the so-called queue. And you probably all heard about queues before. You have been in queues many times. And we're considering the so-called FIFO queue, the first in, first out data structure, which is collecting sequential entities where we have an NQ and a DQ operation. NQ means we're adding something to the queue, and DQ means we're removing something from the queue. And the special thing here is that we NQ at one side, at the back of the queue, and we DQ from the other side, from the front of the queue. So there's new elements coming from the back, and we're removing the oldest elements in the queue in the front. Such queues can be efficiently implemented via linked lists, and the NQ and DQ operations have a time complexity of O of 1, so constant time complexity. It's very, very fast to add elements to the queue or to remove elements from that queue. Now, how does the breadth-first search algorithm works? We first define the so-called open queue, and then we define 2 additional variables. One is the so-called closed set variable, and then we have a dictionary that's called predecessors. The open queue is storing all the elements that we still need to work on or still need to work through, and the closed variable is the set of all nodes in the graph that we haven't that we already have processed, and the predecessors are is a list of elements, of sequential elements that we need later on to backtrack the result. So we're going to use that as an intermediate storage memory for storing how to backtrack later once we've found the path. So let's start. The first thing we do is we have our source element that we add to the open queue. We NQ the source element S. And then while the open queue is not empty, we do the following. We remove, we dequeue one element from the open queue. We call that element U. If U is the sink, the target, then we simply return the path, which can be extracted from the target, from this sink node U, and the predecessors list, which stores how we can move backwards to the source node. But that's typically not happening in the first step, right? Because otherwise we would have already, if the first thing that we're gonna dequeue in the beginning would be the sink, then the source and the sink would be the same, right? That's typically not happening. So we're gonna skip that step in the first iteration of this algorithm. And what we're instead gonna do is, for all the successors of that node that we have dequeued, in this case in the first step S, we're gonna go through the set of successors and do the following. If the successor is not in the closed set yet, and if it's not in the open set yet, then we're gonna NQ it into the open queue, and we're gonna add the node U to the predecessor dictionary at key V. And then finally, we're going to add node U to the closed set because we have processed it. And that's it. Okay? So let's see how that works more concretely in an example. I think that simplifies things. So here we have an example graph, which we want to apply our breadth-first search algorithm to. We have the source here and the sink here. And we want to find the shortest path from the source to the sink in terms of the number of edges to be traversed. And we start by putting S into the open queue. The first thing we're going to do is we're going to dequeue S. And S is of course not the sink. So we're going to look at all the successors of S. And none of them is in the closed or open queue already. So we're going to enqueue all of them. So that's what's going to happen here. Right? A, B, and C are going to be added to the open queue in the first iteration. Right? So I'm talking about iterations of this while loop here. Now the next thing we're going to do is we're going to dequeue from that queue here. We're going to dequeue A. We're going to see, well, that A, the successor of A is D. So we're going to enqueue D and set A as the predecessor of D. Right? And then we're going to add A to the closed set because we have processed it already. And D is then part of the open queue. And similarly, we're gonna, for B, we're gonna look at its successor, E. We're gonna add it to the open queue. And we say that B is the successor of E. So this dictionary is not illustrated here. So this is just something you have to keep in your head. This is basically just for backtracking later. And then we're going to close B. And similarly for C, we're going to add T, and we're going to close C. And in this illustration here, I've done all of these 3 steps, 3 iterations in one step. So I fast forwarded 3 iterations to not create too many slides. That's why I have written fast forward here. So if I go back, you can see A, B, C are in the open queue. Now I've processed all of them. They get added to the closed set. And instead I have D, E, and T here in the open queue, right? And now I apply the same algorithm again. First, I'm gonna now dequeue D, the node D. And the successor of D is T. But T is already in the open queue. So I'm not going to add it to the open queue again. So I'm going to just simply add D to the closed set. I'm going to add E to the closed set as well. And finally, I'm going to process T, which is the sink node. And I have found my final path. I have the closed set S, A, B, C, D, E. And the final path now is SCT, which has been found through backtracking by extracting the path. So now I have reached T finally. So I'm in line 5. And I'm executing line 6 here, which is extract the function extract path. I'm going to go through all the predecessors through this linked list backwards. From T, I know the predecessor is C. From C, I know the predecessor is S. So I can backtrack. And so I know this path here now. And this is the shortest path. SCT, there's no other path that's shorter. You can see if I go from S to C to A, D, T, that's not shorter. If I go from S to A, D, T, that's also not shorter, etc. Right? Oh yeah, maybe one thing that I forgot to mention before is that here I have 2 red arrows. What does this mean? Well, as I mentioned, when I'm processing B, I'm adding E to the open open queue, but C is already in the open queue, or it's actually already processed. It's already in the closed set now. Well, no, actually, while processing B, C was still in the open set, so I'm not going to add it to the open set again. And similarly, when I'm processing C, then A is already in the open queue because I've added it to the open queue directly from S. So I'm not going to add it to the open queue again. This is the condition here in line 8. And that's why these two arrows here are red, right? Okay, so I found this path here now. This is breadth first search. This is great. I have an algorithm for finding the shortest path. But what's the problem with this? The problem is that unweighted graphs, as we considered so far, cannot represent road segments of variable length. So how can we solve this? Well, one naive solution would be to chunk the road network into small segments of equal length and then run the same algorithm there. But the problem is that this just increases computation a lot, which we don't want to do. So is there a better solution? There is, and it is to use weighted graphs. So here we see a weighted graph, where each edge carries a weight corresponding to the road segment length or travel time. In this particular case, we have the source here and the sink here, and I've chosen these weights here as the Euclidean distance between two nodes that are connected by that respective edge. So for example, S to A has a distance of 2, A to T has a distance of 1, and C to S has a distance of roughly 1.1. This is the Euclidean distance. Oops, too quick. Good, but now of course we need a new algorithm to solve this weighted graph problem. And there is an algorithm luckily for this. This is the famous Dijkstra shortest path algorithm that you've probably heard of before. Before looking at the algorithm, I want to show you an anecdote that I found on the internet on the discovery of Dijkstra's shortest path algorithm that was communicated from Edgar Dijkstra in an interview with Communications of the ACM. What is the shortest way to travel from Rotterdam to Groningen? In general, from given city to given city. It is the algorithm for the shortest path, which I designed in about 20 minutes. One morning I was shopping in Amsterdam with my young fiancée, and tired we sat down on the café terrace to drink a cup of coffee. And I was just thinking about whether I could do this, and then I designed the algorithm for the shortest path. As I said, it was a 20-minute invention. In fact, it was published in '59, 3 years later. The publication is still readable. It is in fact quite nice. One of the reasons that it is so nice was that I designed it without pencil and paper. Without pencil and paper. I learned later that one of the advantages of designing without pencil and paper is that you're almost forced to avoid all avoidable complexities. Eventually, that algorithm became, to my great amazement, one of the cornerstones of my fame. Okay, so let's look at the Dijkstra algorithm now. And before we do that, we have to introduce a new data structure, which is the min-heap. The min-heap is a specialized tree-based data structure. An example of this you can see here on the right. It follows the so-called min-heap property, which is the value of any node in the tree, any node in that tree, is smaller than any of its children. So for example, 1 is smaller than any of these, or 17 is smaller than any of these. It's an efficient implementation of a priority queue, where the element with the highest priority, in this case the smallest element, is always in the root node, located at the root node. So the smallest element is stored at the root node in a min heap. It is a partially ordered data structure, but it is not entirely sorted. The common implementation for this data structure is a binary tree. And the nice thing about this data structure is that inserting an element into that min heap or removing the first priority element, the smallest element, has log n complexity. So it's rather efficient. So we're going to use this min heap data structure where we have elements arranged in a tree with a particular value that determines where they are arranged in that tree, and the element with the smallest value is always on top. But of course, these elements could have some other attributes other than just this value, could carry some other data, which they do, as we'll see. It's not just the value itself. The value is just determining the priority, basically. We're going to look at the Dijkstra's shortest path algorithm by comparing it directly side by side with the breadth-first search algorithm that we've seen before, which is illustrated here on the left-hand side. All of the operations that differ from the BFS algorithm, that differ in the Dijkstra's algorithm from the BFS algorithm, I highlighted in red here to better see the differences. So let's start. The first thing we are going to do is we are going to allocate the variables. Again, we have a closed set and a predecessor dictionary, but now we have not an open queue, but an open min heap. And instead of just enqueuing the source, we are pushing to that min heap. So the operation to add something here is called push. We're pushing the source element, and we're pushing it with a value of 0. This value here indicates the distance to that node from the source. Because we're pushing the source node itself here, we're pushing s, 0, because the distance from the source node to itself is, of course, 0. While the open min heap is not empty, we execute the following. We are removing the top priority, the smallest element, from the min heap. This is similar to the dequeue operation, but now we're not just dequeuing from a queue, but we are removing the highest priority element from the min heap, where the priority is simply this cost, so the element with the smallest cost. And so I've written this here in terms of Pythonic notation, where we are obtaining from this pop operation u, the node itself, and the cost. In this case, in the first iteration, we would obtain u equal s and u cost equals 0. If u is already the sink, then we return the extracted path as before. But of course, again, here this is not going to happen in the first iteration typically, because otherwise the source must be equal to the sink. So we're in this case normally in the beginning. For all successors, we do the following. If the successor is not in a closed set, then we're computing the edge cost from u to v and call this uv cost. If v is in the open set already, then we check if the cost to element u, to node u, plus uv cost, the cost from node u to node v, this is the weight, the number that is at the edge in the weighted graph, is smaller than the cost that is stored for element or for node v in the min heap. If that's smaller, right, because it's already in the min heap, there must be some cost stored in there, right? So it's already in the min heap. If it's smaller, then we are simply updating it, because what this means is we found another route to that node v now, which has an overall smaller cost if we go through this other route compared to what we have previously discovered. So we're simply updating the value of v in the open min heap. And we are also updating the predecessor list. We are saying, well, the predecessor of v is not like what it was before, but it should be u, because we have found another node u through which we can move more quickly to v. If it's not already in the open min heap, if v is not already in the open min heap, we simply push v to the open min heap, and we store for v the costs that were required to get from the source to node u, which is u cost, plus the edge cost uv. So this is the total cost now, the best cost we've discovered so far for reaching v. And we are also storing the predecessor of v to be u. And that's it. And we add u now to the closed set because we have processed it. And in the next iteration, we are looking again at the top priority element of the open min heap, which is now the next node in that min heap. Good, that's all. So here's the algorithm again on the left, and let's look at a concrete example on the right, where we have this neat little graph here with source and sink. And now, as you can see, we have not just directed edges, but we have weighted directed edges, where each of these directed edges has a weight. For example, 2 is the distance from S to A, or 1 is the distance from A to T. Let's start. We start with adding S to the open min heap, and the cost to vertex S is 0, because S is this source, it's the starting point. So the first thing we do is we're going to process S. We're going to add S to the closed set. And because B and A are successors of S, we're going to add B and A to the open min heap. And of course, the cost to move to B is the cost for being an S, which is 0, plus this edge cost. So it's 1. And the cost from S to A is, 0 plus 2, so it's 2. And here I have already sorted that list so that I can always pop this smallest element here. So in this case, it's actually, it's even a little bit more than the min heap. It's basically just a sorted list, so it's easier to run through. But really, the only requirement we have is that this is the first element. The smallest one must be the top element. Good. Okay, so we have B and A in the open min heap. So we're processing now B first, because B has a smaller value than A. So it's more likely to reach the target first. But maybe it doesn't. So let's see. So what happens now? Well, the successor of B is C. The distance to C is 0.5. So we are adding C to the open min heap with a cost to vertex 1.5. 1, which was the cost to B, and 0.5, which is the edge from B to C. And because 1.5 is smaller than 2, this is the node from the open min heap that we're going to pop next. Because there's no other successor of B, we're going to add B now to the closed set and continue with the next node from the open min heap, which is C. C now has a successor S and a successor D. However, because we know that S can be reached, because S is already in the closed set, we're not consider it any further, right? So we know already there's no other way we can get to S more quickly, because we have started at S, right? So going to S in 1.5 plus 1.1, which is 2.6, is clearly not as fast as starting at S directly. So this is why this edge here is colored red. And we're not going to add S again to the open min heap. It's already closed. Right. So if we look at the algorithm here on the right, we have this condition. V must not be in the closed set to continue. But this condition is fulfilled indeed for D. It's not in the closed set. And the edge distance from C to D is 2.5. So we're going to add D to the open min heap. And the cost to D is 1.5, which is the cost to C, plus 2.5. So we have 4. Now the next element that we're going to pop from the open min heap is clearly A, because A has a cost to vertex of 2. And if we now continue, we see that like the successor of A is T, and the distance from A to T is 1. So we are adding t now to the open min heap with a cost to vertex of 3, which is 2 plus 1. And now the next element that we pop from the open min heap is indeed the sinc t, because t has a smaller cost to vertex than d. And so we're done. Dijkstra's algorithm is guaranteed to find the shortest path. In this case, SAT, which has a distance of 3. Note that we didn't need to move or didn't need to consider the edge d to t, because we already knew that there is, like, if the cost to vertex d is 4, then like moving through d to the sinc is suboptimal, because we already found a path that's shorter. So we don't need to process this edge at all. This is the core idea of Dijkstra's algorithm. Now, this is great, but what is the problem with Dijkstra? The problem with Dijkstra is that this method is not scalable to very large graphs, because it becomes at some point also very expensive and slow. For example, if you consider a graph at the extent of the map of New York City, which has approximately 54,000 vertices and 140,000 edges. So what can we do in this case? Is there something even more efficient than Dijkstra's algorithm? And it turns out that for problems, for spatial problems, spatial graphs, it is, because we can introduce a useful heuristic that tells us in which direction to move if we don't know. So we're introducing a so-called planning heuristics. So an example is to use simply the distance to the target as a heuristic to select promising vertices to expand. How does this work? Let's look at a concrete example. Euclidean planning heuristics exploits a structure of planar graphs. The idea is that the straight line between vertices is a useful estimate of the distance along the path. For example, if I want to move from A to T, the Euclidean distance in this case, as I measured it, is 6.7. Of course, the true distance, if I want to move from A to T, is 5 plus 2, it's 7. It's not exactly 6.7, but 6.7 is a good approximation to that distance. So it's a useful estimate to know roughly, if I'm at node A, how much, like how long would be the distance to node T, right? Okay, so in this example here, Dijkstra's algorithm would expand from S to A, right? Because 1.9 is smaller than 2. But of course, if we look at the graph, if we want to go from the source to the sinc, this is very likely not the optimal way to go. But Dijkstra algorithm doesn't know that. It doesn't exploit spatial properties. So it doesn't know that B is more likely to be on the shortest path as it's closer to the target T. The so-called A-star algorithm that we're going to introduce now uses this heuristic to plan more efficiently. And the nice thing about this algorithm is that it always returns the optimal solution, independent of the chosen heuristic. I'm sorry. So let's move to the A-star algorithm now. I hope my voice is making it to the end of this unit. So here we have a comparison of the A-star algorithm and Dijkstra's algorithm. You can see that we again have an open min heap, a closed set, and a predecessor dictionary. But in this case, we're adding a not just a tuple, like a pair to the open min heap, but a free tuple, a triple to the open min heap, which is the source node here in the first step, the cost to the source node, and the heuristic from the source node to the sink, which we call h of s. So what we're then going to do is while the open min heap is not empty, as before, we're going to pop an element from that min heap, but now this element is popped based on the cost plus the heuristic. So the min heap is sorted or arranged based on the cost plus heuristic, not just the cost as before. So u cost and u heuristic together are the smallest element that we pop from the open min heap. So we call this u cost, and u heuristic. Again, if u is the sink, then we return the final path through backtracking through the predecessors. And otherwise, for all successor nodes, we do the following. It's very similar to before. If the successor is not in the closed set, then we're extracting the edge cost from u to v. And if the successor is in the open min heap already, then we check now, and this is where the difference comes in, if u cost plus uv cost, which is the cost from the source to the node v through node u, plus the heuristic from node v to the target, which we call h of v, is smaller than the full cost from the source to the sink that combines the cost to v plus the heuristic that's already stored in the open min heap for v, right? This is what this function full costs here extracts. It's basically looking up that node v in the open min heap, and it's extracting the v cost and the v heuristic and adds them together. And so if this cost here with the heuristic together, but going through this other node u, v must have been added through some other node before, right? So now we're trying to add it, or to check the distance if we go through node u to node v, if that cost is smaller. And if that is smaller, then as before, we're going to replace it. We're going to replace the costs in the open min heap for node v by this new cost, and also the heuristic by the new heuristic. And we're going to update the predecessor of v to be u. Now, if v is not already in the open min heap, then we're simply going to add it to the open min heap with, again, the cost to node v and the heuristic, which is the cost, the approximated cost, or the expected cost from node v to the sink. And we're also going to set the predecessor of v to be u. And then finally, we say that u has already been processed, so we're going to add it to the closed set. Okay? So the only thing that has changed to before is that we have introduced this heuristic, and we're now removing elements from the open min heap, where the priority is now based not only on the cost to that node, but on the sum of the cost to that node plus the heuristic from that node to the target. For example, this Euclidean distance from that node to the target, which provides a good estimate of if that node is likely to be successfully moving our path into the right direction. So this is what we are going to use as the criterion, this cost to the node and the heuristic to the sink, to the target, together we're going to use to determine which node to traverse next and which is the most optimal path. And the nice thing about this algorithm is that it will always, it will also, like the Dijkstra algorithm, find the optimal path, but it will very likely find it faster than Dijkstra's algorithm. We're going to see an example. So here is the same example from before. Now we're going to run the A-star algorithm here on the left. We're going to start with the open min heap, where now we're inserting node S, but we are not going to insert the cost to node S, but the cost plus the heuristic to the sink, which is the cost to node S is 0 plus the estimated distance is the Euclidean distance from S to T is 3. Now we're going to pop that node S from the open min heap, and we see that B and A are successors, so we're going to add node A and node B to the open min heap. And in this case for A, we have a cost plus heuristic of 3 because the cost to A is 2 and the heuristic from A to T is 1. But for B, we have a cost of 1, 0 plus 1. And the heuristic for B to the sink is, in this case, 3.2, which is the Euclidean distance from here to here. It's not illustrated, but I just tell you it's 3.2. So 1 plus 3.2 is 4.2. And now we're popping node A because that's the more likely one. And we see that the successor of A is T, and the distance to T is now really 3. So we don't need any heuristic anymore. We have the distance 2 plus 1, which is 3. And we can see that this distance here is smaller than the cost plus the heuristic for node B. So we don't need to continue with node B because we know that the true cost along that path can only be higher than the cost plus the heuristic. So we're not going to expect a smaller number than 4.2 if we go through node B and try to reach T. So we have already reached the optimal solution, and this is what we're going to return. S, A, and T with a cost or distance of 3. And so if you compare this to the Dijkstra algorithm, you can see that we didn't need to expand node B any further because we have discovered T much faster. We started with A and then directly progressed to T. So let's look at a slightly more complex example, and I found this very nice Java application from Kevin Wang called PathFinder, which is comparing the A-star and Dijkstra's algorithm. And you can very nicely see the, that's maybe a little bit too large. Let's make it smaller. You can very nicely see the complexity. So let's start by generating a map, and let's set a target location. This is the target location. And now we're moving to the path search option, and we're setting the start location here. And we can now compare what happens for the A-star and for the Dijkstra algorithm. So what you can see is that because the Dijkstra algorithm is uninformed in which direction the goal is located, it expands in all directions, while the A-star algorithm expands more rapidly into the actual target location. So let's generate a new map. Why does it disappear? Now maybe let's put the target here. And let's start here. And again, we can see how the A-star algorithm finds the target much more quickly, connects the source with the sink much more quickly than the Dijkstra algorithm, which needs to visit much more nodes. The visited nodes are illustrated in purple here.